So this segment of the lecture will be dedicated to contour integrals and the Gaussian integral. So before we discuss contour integrals, let's discuss the two theorems that we'll be using. So number one, so consider a contour on a complex plane. The contour integral of some analytic function on a complex plane. So f of z is some analytic function. So what does that mean? It means that it satisfies the Cauchy-Riemann equation on all points on the complex plane except maybe some isolated points where it blows up. So the Cauchy-Riemann equation, let me remind you, is given by this. So so we have the function and suppose that the function has these points on which it is singular. So this is say x1, x2, x3, x4, x5, x6, x7, so on and so forth. And now suppose that we have a contour which covers some of these, encloses some of the singularities, and we do a contour integral. So the contour integral is taken counterclockwise. So what is this object? So let's call this contour, say gamma, then the contour integral is gamma f of z d of z. How do we evaluate this integral? Well, Cauchy gave us a very nice theorem which we can use to evaluate this integral. What Cauchy told us is that this contour integral is given by the sum of the residues times 2 pi I of the function at the points x equals to xi, where we are only summing over those singular points xi which are contained inside this contour. So we are not looking at the residues of this at this point or this point. Okay? So if you don't know what residues are, I suggest that you go back to your complex analysis course and review that. Roughly speaking, a residue is if you have a Laurent series expansion of a function, then residue is the coefficient of the term which is the 1 over z minus z naught term. So here I'm kind of mixed up my notation a little bit. I'm using x and z to kind of call the same thing. So maybe I should correct that. Okay, let me do that. This should be z, and this is z equals to zi, and these should also be z's. I'm just too lazy to change them. All right, so this is Cauchy's, that was famous Cauchy's residue theorem. It's remarkably easy to prove. Anyway, the other theorem that we're going to be using is Cauchy's integral theorem. And that theorem is also very easy to prove. And what does it say? What it says is that suppose we have an integral, a complex integral of the analytic function over some limit a to b over some path, some contour. So a is a point here. So let's call this, say, C. I'm sorry. Let's call it C. So we have some, it starts here and it ends here, and C is some path. So what we're doing is that we're taking this integral over this path between these 2 points, Now, suppose that I now deform this path without changing the endpoint. So I deform this path to a new path. Let's call that C prime. But in this deformation process, so in going from here to there, in this deformation process, I do not cross any singularities of f of z. So basically, this region, which I have denoted, say, by green here, there is no singularity of the analytic function f of z. If that is the case, then Cauchy's integrals theorem tells us that, it's the value of this integral doesn't change. Okay? So that means that we can just deform the paths as we like, as long as we don't cross a singularity of our function. So we're going to use these two theorems in evaluating the integrals that we want to evaluate. The first integral that we want to evaluate is connected to the top hat function and the sinh function. And there we used the result that this there were some constants, but those constants can be absorbed by redefinitions. And so we want to first prove this. So the first step in proving this is actually not to do a contour integral, but to just do an integration by parts and make it a bit simpler. So let me remind you what integration by parts means. So this, we have two functions, f and g, and we have got the product and we're integrating them. So we have to integrate one of those guys. And the other one, we differentiate. All right? So this is our integration by parts formula. So now if I take f of x to be sine squared of x and g of x to be 1 over x squared, then 1 by pi, integrate from minus infinity to plus infinity, sinh squared of x by x squared of dx will first give me a term which is going to be x squared, some integral over sine squared of x dx, but the limit is from minus infinity to plus infinity, and because of that this is going to go to 0 because this is going to give you 0. And then the second term is going to be the interesting term, and here the differentiation of g of x, f of f prime, the integration of g of x is going to give me minus 1 over x here, and then the differentiation of sine square is going to give me sine of x cosine of x d of x. So we can rewrite this as so there was a 1 over pi which I forgot to write here. So there's a 1 over pi, and then these two minus signs give me a plus sign. So this comes minus plus to plus, and then we have these two can be combined into sine of 2 of x, and then there's x d of x. Of course, we can just multiply this by 2 and multiply this by 2. Then what we have here is pi, 1 over pi minus infinity to plus infinity. And we can redefine 2x to be x. So we just have x. It's like magic. We had squares. We had squares here. And somehow we got rid of the squares. And so We still haven't done our integral. We just wrote it in a form that is going to be more convenient. And so what we want to show is this. We want to show that this thing, sine of x over x of d of x, is going to be pi. How do we do this? Okay, let's take a complex integral. Let's take, but evaluate it on the real line. So we have some complex function, but we are doing the integral over the real line. And we know that this is a very nice function, sinh function. There is no singularity at x equals to 0. So now by using Cauchy's integral theorem, we can actually deform the contour. So what was the contour? The contour was, it was coming from minus infinity and then going off to plus infinity. And over here, there was z equals to 0 and the integral direction was something like this. But then what we can do is that we can say, okay, let me just use Cauchy's integral theorem to deform this contour such that I just want to avoid the origin. No harm done, because in doing this deformation from here to here, I have not encountered any singularity of my analytic function, which is the integrand. So let's call this new contour C, or this, and then what happens is that this integral of ours, let's call it I, this then becomes I equals to C. And now I'm going to write the sine function in terms of exponentials. So I can write it as e to the power iz minus e to the power minus iz divided by 2I. And then, of course, the z was there before. We can factor out our 2I, and then we can write out these two terms as two different integrals, e to the power iz over z d over z, and then we have minus c e to the power minus iz by z d of z. All right, so now if z has a positive imaginary part, that is, if I take z to be in the upper half plane, then as z goes to infinity, e to the power I of z will go to 0. And that's because if you look at it, this thing, if z has a positive imaginary part, it's I times some real number, which is the imaginary part. That I and this I will give you a minus sign. And as z goes to infinity, that coefficient is going to go to infinity. So we'll have e to the power minus infinity. So that'll go to 0. Okay? On the other hand, if z has, a negative imaginary part, then as z goes to infinity, e to the power minus I of z will go to 0. So why do we need these facts? We need these facts because what we're going to do is that we are going to take this first integral. So the contour was, just this thing. But then what we'll do is that we're going to close this contour on the upper half plane using a big semicircle, a semicircle whose radius is infinite. Okay? But because on that semicircle, the real part, the imaginary part of z will be positive, that semicircle, the integrand will give you 0. So that semicircle will not contribute anything. But this will turn this open contour into a closed contour. So the first integral becomes this thing. So this is, of course, an infinite semicircle. Okay, so now what we can do, we can use the first Cauchy's theorem, the Cauchy's residue theorem. It's not called the first theorem, by the way. And we can evaluate this integral. And what it says is that, this integral is given by 2 pi I times the sum of the residues of this integrand. So what are the residues? So there's only one singular point, which is z equals to 0 of this function. This function doesn't have a singularity at z equals to 0, but this guy does. So it's what is the residue? So if I look at the function, it's 1 over z e to the power I z. So I just expand. This is a power series, so I get 1 minus I z. Then, I get I squared, z squared, the factorial of 2, blah, blah, blah. All I care about is the 1 over z term. And then, so this is the only 1 over z term. And what is the coefficient of 1 over z? It's 1. So the residue of e to the power I z over z at z equals to 0 is 1. On the other hand, if I now look at the second integral, so here I will, close the contour on the lower half plane so that there is no contribution from that part, so that the total integral is equal to this integral. So if I do this, then from the lower half plane, I don't get any contribution. So we can now evaluate our integral. So the integral had 2 parts. The second part didn't give us any contribution because there was no singularity enclosed by a contour which is closed in the lower half plane because the singularity is outside. And okay, let me just draw that contour for completeness. So for the second integral, we are going to do this this thing, where of course this semicircle has an infinite radius, and there are no singularities here. So so basically, if I call this contour, say lambda prime, then lambda prime, this is a closed contour e to the power I z by z d of z, that is going to be 0. Okay, so so if I combine these results, then my original integral is, there was a 1 over 2 pi, and then Cauchy's theorem gives me a 2 pi I times 1, which was my residue. Therefore, I get a pi here. So, but this is just an integral over the real line, so this function, this complex variable z here is just x. So we get, as a result, and of course, that means that we get this thing. So that is our first result. So for a second example, using contour integral, we are going to, remember that when we obtained AK from the Gaussian, from psi k, where psi k was the Gaussian, it had the form of x squared by, was there 2 or something like this? You had to do an integral which was of this form. So this is not something I showed in the lecture, but if you go through it, you will find that you have to do an integral which is of this form. So this is like a Gaussian integral, but it's got an imaginary part. So there's an imaginary part. So the question is, can you still do a Gaussian integral? Can you just use the result of Gaussian integral that you probably know. There is no guarantee. That's the answer. So to do this, you have to, you actually have to do this carefully. So to do this, let's look at the complex integral over some contour, which I will specify in a minute. So e to the power minus 2 sigma squared. And instead of x here, I get a z plus ik sigma squared dz. So let's specify this contour. So this is going to be a contour which will be like a rectangle. So it goes from minus r to plus r, and then it goes, sorry, I should make sure that the x-axis is coincident. So this is the x-axis, and the red is the contour. Right. So this is my contour, and this goes from minus r to plus r over here, and here it goes from r to minus arc this 2. So this is C, the contour that I am doing this integral over. So what I can now do, so there is no, like, this is a very nice function, so there is no like singularity here, so we are not going to be using the residue theorem. So now let's just express this integral. So this so because there's no, this is a closed contour of an analytic function, and there is no singularity inside, so this integral is 0. So we can write different parts of this integral. We can break this up now, and then if you break it up, then on one side we have this thing, e to the power minus 1 over 2 sigma squared z plus ik sigma 2 squared d of z. And then on the other side, I'm just going to specify the limits because the integrand is going to be the same. So we have one going from r to r minus ik sigma 2 dot dot dot. Another one which goes from r minus ik sigma 2 to minus r minus ik sigma 2. And then there will be another part which will be going from minus r minus ik sigma 2 to minus r. Okay? And then what we do is that we take r to infinity. Okay? So we just make this go bigger and bigger. If I do that, then see that what happens? What happens is that, this integral and this integral, they go to 0. And therefore, only this guy is left. And therefore, what happens is that our original integral, which is we are trying to evaluate, is, this guy. That thing becomes minus infinity minus ik sigma squared, and then plus infinity minus ik sigma squared e to the power minus 1 over 2 sigma squared z plus I sigma 2 sigma squared, there's a k here, squared of dz. And now we are in a position to make a variable transformation. We can introduce a variable which is u, and it's given by z plus I sigma squared of k divided by square root of 2 of sigma. And if you do that, then our integral becomes square root of 2 sigma minus infinity to plus infinity e to the power minus u squared d of u. And this is integral, we know this is just the Gaussian integral. And that gives me 2 sigma square root of pi, and this is going to give me square root of 2 pi sigma. So lastly, we're going to do the Gaussian integral. Most of you know how to do this integral, but some of you may not have seen this, and this is something you need to know. So the Gaussian integral is this guy. And we want to evaluate this. I want to show that this is equal to square root of pi. So to do this, let's square the integral. So if I square the integral, u is a dummy variable because I'm integrating over it, so I can replace it by some other variable, say v. Right? So and then what we can do is that, okay, we can say, let's introduce 2 new variables, say r. R is, say, u squared plus v squared. So you can think of u and v as being the x and y axis of a 2-dimensional plane. And r is the radial variable. So, and you'll have some angle theta. And so the angle theta would be given by tan of theta, and that'll be given by v over u. So if I transform this integral into my polar coordinates, then this will be given by a double integral where r goes from 0 to infinity and theta goes from 0 to 2 pi. And the measure, as you know from curvilinear coordinates, Jacobian calculus class, is r dr d theta. And then our integrand now becomes e to the minus r squared. Of course, the integrand doesn't depend on theta, so we can do that integral. So we get a 2 pi. So what we have left over is 0 to infinity r e to the power minus r squared. Of course, what we can do is that and then there's a dr, of course. We can do is that we can go pi 0 to infinity, and we can write this as e to the power minus r squared d of r squared. So we can redefine r squared to be just x, and if we do this integral, this is nothing but pi, and therefore the integral that we were trying to evaluate is square root of pi. So this brings us to the end of this diversion on contour integrals and the Gaussian integral.